We begin our story not with an object, but with an absence, a gaping silence in the otherwise rhythmic harmony of the solar system. For centuries, our solar system was perceived as a perfect, orderly clockwork. But nestled between the orbit of the small, dusty red planet Mars and the colossal, gas-shrouded giant Jupiter was a mysterious, immense void, a distance spanning hundreds of millions of kilometers, or nearly 186 million miles. This enormous, seemingly empty expanse was one of the greatest geometrical riddles of the heavens, hinting at a missing piece in the celestial puzzle, a planet that ought to be there, but simply was not. It was a blank canvas that would eventually be filled not by a single world, but by a chaotic, scattered collection of countless tiny ones, creating a dynamic, rubble-strewn frontier we now call the Asteroid Belt, a place of immense geological significance and a frozen archive of the solar system's tumultuous youth. As we journey through this celestial expanse together, following the footsteps of astronomers who first sought to fill this gap, I invite you to join the conversation. Tell us where you are listening from and what time it is. And please subscribe so you are notified of future stories as they unfold. This quest to locate the phantom planet was driven largely by a curious numerical pattern that enchanted 18th century astronomers, a predictive framework for planetary distances now known as the Titius-Bode law, named for the German astronomer Johann Bode, who popularized the concept, and the Prussian mathematician Johann Daniel Titius, who first articulated the sequence in the 1760s. The rule suggested a surprisingly regular spacing among the known planets, starting with a sequence of zeros, threes, sixes, 12s, and so on, each number doubling the last and adding 4 to each result before dividing by 10. The formula produced values that closely matched the known average orbital radii of Mercury, Venus, Earth, Mars, and the newly discovered Uranus. The predictive power of the pattern was undeniable, yet it left one conspicuous anomaly: a perfect, unmissable slot for a planet orbiting at a distance of nearly 3 astronomical units from the Sun, or roughly 450 million kilometers, about 280 million miles, a planetary vacancy between Mars and Jupiter. The conviction that a celestial body must occupy this station grew so strong that by the close of the 18th century, a dedicated and formidable group of sky gazers took action. They formed the Vereinigte Astronomische Gesellschaft, or the United Astronomical Society, which quickly earned the nickname the Celestial Police. This determined international consortium, initially led by the Hungarian nobleman Baron Franz Xaver von Zach, set out on a systematic search. They strategically divided the zodiac, the band of the sky where planets are found, into 24 precisely measured segments, assigning one section to each participating astronomer. The primary mission of these celestial detectives was clear: to finally locate the missing world, bringing order and completion to the solar system's mathematical architecture, and confirming the profound implications of the Titius-Bode relationship. The exhaustive and painstaking search began in earnest, an ambitious campaign of observation that would soon be unexpectedly and completely circumvented by a stroke of accidental genius. The celestial police had yet to claim their prize when, on the very first night of the 19th century, an Italian priest and astronomer working alone beat them to the discovery. The man who would claim the honor was Giuseppe Piazzi, director of the Palermo Astronomical Observatory in Sicily, who, on January 1st, 1801, was meticulously charting stars in the constellation of Taurus. Piazzi was not initially looking for a planet, but rather compiling a star catalog, an exacting and necessary task that demanded extraordinary precision. And it was through this methodical work that he noticed a faint, star-like object moving ever so slightly against the fixed stellar backdrop. This movement, slow but definite, was the undeniable signature of an orbiting body much closer than any distant star, and its orbital mechanics placed it precisely in the mathematical gap the celestial police were searching so diligently to fill. Piazzi initially exercised great caution, tracking the object for over a month and corresponding with fellow astronomers, at first suggesting he had discovered a new comet. Comets were known entities, celestial wanderers with predictable, if sometimes dramatic, appearances. But this object showed no sign of a coma or a tail, the characteristic features of a cometary body. It was a sharp, distinct point of light, behaving with the calm and stately motion of a planet. His observations were cut short in mid-February, when the object's trajectory carried it too close to the sun, losing it in the solar glare. The scientific community was left with Piazzi's tantalizing but incomplete data, and the great fear was that the newfound world would be lost forever, its orbit not sufficiently calculated to predict its reappearance. The challenge fell to a brilliant 24-year-old German mathematician named Carl Friedrich Gauss, who, upon hearing of the dilemma, developed a revolutionary new method for calculating an orbit from only a handful of observations. Gauss's powerful technique, a mathematical tour de force, produced a precise prediction for where the object should be found once it emerged from behind the sun. In December of that same year, using Gauss's calculations, the Baron von Zach, the very man who had organized the celestial police, successfully relocated the object, confirming its existence and securing its place in the solar system. Piazzi, as the discoverer, was granted the right to name his find. He christened it Ceres Ferdinandea, honoring both the Roman goddess of agriculture, who was the patron goddess of Sicily, and his own royal patron, King Ferdinand of Sicily. The second part of the name was soon dropped for political reasons, but Ceres remained, and for a brief time, it was celebrated as the 8th planet in our solar system, the missing world that perfectly satisfied the Titius-Bode law, finally bringing a sense of completeness to the cosmic order. This tidy conclusion, however, was shattered just over a year later. In March of 1802, Heinrich Olbers, a German physician and a dedicated member of the Celestial Police, was observing the region of the sky where Ceres had been found when he stumbled upon another moving object. Its orbit was remarkably similar to that of Ceres, occupying the same supposedly empty gap between Mars and Jupiter. This second body was named Pallas, after the Greek goddess Athena, and its discovery created an immediate and profound crisis in cosmology. The Titius-Bode law had predicted a single missing planet, not two. Olbers himself proposed a radical and dramatic explanation: that Ceres and Pallas were not planets themselves, but were instead fragments of a much larger single planet that had, at some point in the distant past, catastrophically exploded or been shattered by a cosmic impact. This disruption theory was incredibly compelling and seemed to explain the presence of multiple bodies in the same orbital zone. The theory gained even more traction when, in 1804, a third object, Juno, was discovered by Carl Harding. And then, in 1807, Olbers himself found a fourth, which he named Vesta. For nearly 4 decades, these 4 small worlds were listed as planets in astronomy textbooks, bringing the total count of planets in the solar system to 11. Yet, as telescopes improved, it became clear that these bodies were fundamentally different from the classical planets. The great astronomer William Herschel, the man who had discovered Uranus, was among the first to argue that they did not belong in the same category. He noted that even in his powerful telescopes, they appeared as small points of light, just like stars, and he was unable to resolve them into visible disks the way he could with Jupiter or Mars. In 1802, he coined a new term for these objects: asteroid, from the Greek word asteroides, meaning star-like, a name that would stick for centuries. The idea of a single, shattered planet, often referred to by the hypothetical name Phaeton, held sway for almost 150 years. But as our understanding of planetary science deepened in the 20th century, serious flaws in the theory began to emerge. First was the issue of mass. If you were to gather up every single known asteroid in the belt today, from the colossal Ceres down to the tiniest specks of dust, and combine them into a single object, their total mass would be only about 4% of the mass of Earth's moon. This is far too little material to have ever constituted a major planet. Secondly, the chemical compositions of the asteroids are incredibly varied. Different asteroids show evidence of having formed in very different thermal and chemical environments, some rich in water and carbon, others almost purely metallic. Such diversity is difficult to explain if they all originated from the fragmentation of a single uniform parent body. The modern understanding of the asteroid belt's origin is less dramatic than Olbers's explosive hypothesis, but far more fascinating and it points not to a planet's destruction, but to its failed creation. The story begins 4.6 billion years ago, in the swirling protoplanetary disk of gas and dust that surrounded our young sun. Tiny dust grains began to clump together, forming pebbles, which in turn stuck together to create kilometer-sized bodies called planetesimals. Throughout the nascent solar system, these planetesimals continued to merge and grow through a process called accretion, eventually forming the rocky planets like Earth and Mars. In the region between Mars and Jupiter, this process also began, with planetesimals growing into larger bodies, some reaching the size of small worlds themselves. The crucial difference, however, was the titanic presence of Jupiter, the first planet to fully form, and by far the most massive. The gravitational influence of this gas giant was immense, a relentless and disruptive force that stirred the region into a state of perpetual chaos. Jupiter's gravity sent powerful resonances sweeping through the asteroid belt, gravitational nudges that occurred in specific, predictable orbits. Any planetesimal that strayed into one of these resonant zones would be destabilized, its orbit becoming highly eccentric or stretched until it was either flung out of the solar system entirely or sent on a collision course with another object. These powerful resonances, known today as the Kirkwood gaps, are still visible as empty lanes within the belt, swept clean of asteroids. Furthermore, Jupiter's gravitational stirring dramatically increased the relative velocities of the planetesimals. Instead of gently bumping into each other and merging, they began to collide with catastrophic violence at speeds of several kilometers or a few miles per second. At such velocities, collisions were no longer constructive, they were destructive. The aspiring planet was perpetually smashed back down into rubble before it could ever grow large enough for its own gravity to hold it together. The asteroid belt, therefore, is not the graveyard of a deceased planet, but the cradle of a stillborn one, a collection of primordial building blocks that were denied the opportunity to ever complete their planetary journey. This cosmic rubble field, though often depicted in science fiction as a dense, treacherous swarm of tumbling rocks, is in reality a place of almost unimaginable emptiness. The total volume of the main asteroid belt is enormous, and the countless objects within it are spread incredibly thin. The average distance between any two sizable asteroids is well over 1.5 million kilometers, or nearly 1 million miles, a distance almost 4 times greater than that between the Earth and its moon. A spacecraft journeying through the heart of the belt would be exceedingly unlikely to even accidentally encounter an asteroid, let alone have to navigate a perilous slalom course. To date, every probe sent through the region has passed through without incident, their trajectories planned based on efficiency, not on dodging a celestial minefield. Within this vast emptiness, the asteroids themselves are sorted into broad categories based on their composition, which tells a story about where in the primordial solar nebula they originally formed. The most common type, making up over 3/4 of the belt's population, are the C-type, or carbonaceous, asteroids. These are among the oldest and most primitive objects in the solar system, with surfaces as dark as coal, reflecting very little sunlight. They are rich in carbon, organic compounds, and water-bearing minerals, and are most prevalent in the outer regions of the belt, suggesting they formed farther from the sun in a cooler environment. In the inner part of the belt, closer to Mars, the S-type, or silicaceous, asteroids are more common. These are brighter, stony bodies composed primarily of silicate materials and nickel iron, representing material that formed in a warmer part of the nebula. Finally, there are the M-type, or metallic, asteroids. These are the rarest of the main groups and are thought to be the exposed iron-nickel cores of much larger protoplanets that were shattered in those ancient, high-speed collisions. These metallic remnants are, in a sense, the exposed hearts of failed worlds, offering us a direct glimpse into the processes of planetary differentiation that shaped our own world's core. Among these fragments, one body stands out as a true survivor from this violent era: Vesta. It is not just a fragment, but a largely intact protoplanet, a fossil from the dawn of the solar system, with its own core, mantle, and crust, a miniature world that somehow weathered the storm of Jupiter's making. This unique status as a preserved protoplanet means Vesta carries the scars of its long and violent history directly on its surface, none more spectacular than the colossal impact basin that dominates its southern hemisphere. This feature, named Rhea Silvia, is an enormous crater, stretching an astonishing 500 kilometers, or just over 300 miles, across, making it one of the largest impact craters in the entire solar system. The impact that carved this basin, occurring roughly 1 billion years ago, was an event of almost unimaginable power, gouging out an estimated 1% of Vesta's entire volume and blasting millions of cubic kilometers of rock into space. This ejected material did not simply vanish. It was cast into its own independent orbits around the Sun, forming a great swarm of smaller asteroids that still bear the unmistakable chemical signature of their parent. These fragments, now known as the Vesta family, or Vestoids, are a dramatic and visible testament to the belt's violent nature. This concept of asteroid families, great clans of space rock tracing their lineage back to a single catastrophic event, was first pieced together in the early 20th century by the brilliant Japanese astronomer Kiyotsugu Hirayama. While meticulously studying the orbits of newly discovered asteroids, he noticed distinct clusters of objects that shared remarkably similar paths through space, possessing nearly identical orbital inclinations and eccentricities. Hirayama correctly deduced that this was no mere coincidence. These groupings were the scattered progeny of ancient, larger bodies that had been shattered by collisions long ago. Hirayama's insight revolutionized our understanding of the asteroid belt, transforming it from a static collection of primordial rubble into a dynamic, evolving system, a cosmic crime scene where the remnants of past collisions could be carefully analyzed to reconstruct the events that created them. Identifying these families is a work of celestial archaeology. Astronomers use powerful computer simulations to trace the orbits of thousands of asteroids backward in time, watching as the scattered members of a family slowly converge toward a single point of origin, the location of the ancestral impact. The chemical composition of these family members, analyzed through spectroscopy, further confirms their shared heritage, showing they are all chips off the same old block. There are now over 100 identified asteroid families, each with its own story. The Flora family, for instance, is a large and sprawling group of S-type, or stony, asteroids in the inner belt, thought to be the product of a massive disruption that occurred over 1 billion years ago. The Eunomia family, located in the intermediate main belt, is another large grouping, dominated by stony asteroids and named after its largest surviving member, the asteroid 15 Eunomia, which is believed to contain most of the original parent body's mass. Further out, the Coronis family consists of several hundred known members, all sharing extremely similar orbits, and is famous for being the family to which the asteroid Ida and its tiny moon Dactyl belong. These families vary greatly in age. Some, like Vesta's, are ancient, while others are remarkably young in cosmic terms. The Charon cluster, a small subgroup within the Coronis family, is believed to have formed just 5.8 million years ago, a mere blink of an eye in the 4.6 billion year history of the solar system. These ongoing collisions, from the planet-shattering impacts of the distant past to the more recent fragmentations, are the very engine of the belt's evolution, constantly grinding larger bodies down into smaller pieces and creating the streams of dust and meteoroids that occasionally grace our own planet's skies as shooting stars. For most of astronomical history, the story of was asteroid composition was a dry one, a tale of rock and metal, divided neatly into the carbonaceous, silicaceous, and metallic types. The inner boundary of the asteroid belt was thought to coincide roughly with the solar system's frost line, the theoretical distance from the young sun beyond which it was cold enough for volatile compounds like water ice to condense into solid grains. Inside this line, it was simply too warm, and any primordial ice should have long ago been vaporized by the sun's radiation and blown away by the solar wind. Asteroids, being on the inner side of this line, were expected to be bone dry. Comets, the famous dirty snowballs of the outer solar system, were the designated carriers of water ice. This neat picture was completely upended in 1996 with observations of an object named 133P/Elst Pizarro, This peculiar body had an orbit that was completely ordinary, placing it squarely within the main asteroid belt, indistinguishable from its hundreds of thousands of rocky neighbors. Yet, when observed closely, it displayed a faint but unmistakable tail of dust, a feature that was supposed to be exclusive to comets. It was a baffling contradiction, an object with the body of an asteroid, but the soul of a comet. For years, it remained a curiosity. But then, in 2006, a second such object was discovered, and then a third, and it soon became clear that these were not isolated freaks of nature, but the first examples of an entirely new class of celestial body, the main belt comets. These objects, now also referred to as active asteroids, have forced a profound rethinking of the solar system's formation and the distribution of its most vital ingredient for life: water. They are not comets from the distant Oort cloud or Kuiper belt that have somehow been captured into stable asteroid-like orbits. Instead, they are true-born asteroids formed within the belt that have somehow managed to retain significant quantities of water ice deep beneath their surfaces, protected from the sun by a layer of insulating rock and dust. The activity we see, the faint cometary tails, is thought to be triggered by minor impacts from smaller asteroids. These collisions can excavate the surface, exposing the buried ice to direct sunlight for the first time in billions of years. The warmth of the sun then causes the ice to sublimate, turning directly from a solid into a gas. This outgassing of water vapor kicks up surface dust, creating the characteristic tail that trails behind the asteroid for a period of weeks or months before the exposed ice is depleted and the activity ceases. The discovery of these icy asteroids in our own cosmic backyard has monumental implications for the story of our own planet. For decades, scientists have debated where Earth's water came from. The early Earth was a hot and violent place, and any water present on its surface at the time of its formation would have been boiled away into space. The prevailing theory has been that our oceans were delivered later by a barrage of comets and asteroids during a period known as the Late Heavy Bombardment, some 4 billion years ago. The main belt comets provide a perfect local source for this water. Their chemical fingerprint, specifically the ratio of different hydrogen isotopes in their water, is a much closer match to the water in Earth's oceans than that of many comets from the outer solar system. It now seems increasingly likely that it was bodies just like these, ancient, water-rich asteroids from the outer edges of the main belt, that acted as celestial water carriers, seeding our young, arid world with the essential element that would ultimately allow life to flourish. This profound connection between the asteroid belt and the genesis of life on Earth transformed these distant rocks from mere curiosities into vital targets for scientific inquiry, objects that held, locked within their ancient mineral structures, the very secrets of our own origins. To truly understand them, however, we had to move beyond the patient gaze of telescopes and embark on a new age of exploration, one that would see us reach out with robotic emissaries to touch these primordial stones. For decades, the belt was seen not as a destination, but as a formidable barrier, a great celestial reef that had to be navigated to reach the gas giants of the outer solar system. The first vessel to attempt this perilous crossing was NASA's Pioneer 10 probe, launched in 1972. As it hurtled towards Jupiter, mission planners faced a tense and uncertain 7-month journey through the belt's plain. At the time, the true density of the region was largely unknown, and there was a very real fear that the spacecraft could be sandblasted into silence by tiny, untrackable particles, or worse, suffer a catastrophic collision with a larger fragment. But Pioneer 10's passage was remarkably uneventful, and its instruments revealed that the belt's dust environment was far less hazardous than the most pessimistic models had predicted. It emerged into the clear space beyond Jupiter's orbit completely unscathed, proving that the belt was not an impassable wall, but an open frontier. This pioneering success was quickly followed by Pioneer 11, and then by the 2 Voyager probes in the late 1970s, all of which transited the belt without incident, turning a once-feared obstacle into a routine celestial commute. These early Voyagers were merely passing through, their eyes fixed on the grander prizes of Jupiter and Saturn, but the tantalizing glimpses they offered fueled a desire for a closer look. That opportunity finally came with the Galileo mission, which, on its own circuitous route to Jupiter in the early 1990s, was specifically programmed to perform the first ever close flybys of asteroids. Its first target, in 1991, was 951 Gaspra, a stony S-type asteroid. The images Galileo sent back were revelatory, showing a cratered, irregularly shaped body about 19 kilometers, or 12 miles, long, a battered survivor of eons of cosmic impacts. 2 years later, in 1993, Galileo made an even more historic encounter with the asteroid 243 Ida. As the data from the flyby was being analyzed, scientists were stunned to discover a tiny object in orbit around Ida, a moonlet barely 1.6 kilometers, or 1 mile, in diameter. This minuscule companion, later named Dactyl, was a monumental discovery. It was the first definitive proof that asteroids, these supposedly simple chunks of rock, could host their own satellites, transforming them from solitary wanderers into complex, miniature gravitational systems. The existence of Dactyl allowed astronomers to calculate Ida's mass and density for the first time, providing crucial data that revealed it to be a relatively solid, non-porous body, unlike the loosely consolidated rubble piles that some other asteroids are thought to be. The success of these flybys set the stage for the next, more ambitious chapter in asteroid exploration. Not just visiting, but staying. This was the goal of the Near-Earth Asteroid Rendezvous mission, later renamed Near Shoemaker in honor of the pioneering planetary geologist Eugene Shoemaker. Launched in 1996, its target was 433 Eros, a large, elongated S-type asteroid. The challenge was immense. Rendezvousing with and entering into orbit around such a small object, with its feeble and uneven gravity, was a feat of unprecedented navigational precision. After a 4-year journey, on Valentine's Day in the year 2000, Near Shoemaker successfully achieved orbit around Eros, becoming the first spacecraft to do so. For an entire year, it circled the peanut-shaped world, mapping its surface, analyzing its chemical composition, and measuring its gravitational field in exquisite detail. It revealed a stark, alien landscape, dominated by craters, ridges, and a mysterious blanket of fine dust, or regolith, that appeared to be flowing and ponding in the asteroid's low-gravity hollows. As the mission's fuel supply dwindled, the control team decided to attempt a daring and unplanned finale, a slow, controlled descent to the asteroid's surface. On February 12, 2001, the spacecraft gracefully touched down, not only surviving the landing, but continuing to transmit data from the surface for another 2 weeks, giving humanity its first ever up-close analysis from the ground of an asteroid. While Near Shoemaker was rewriting the book on S-type asteroids, another nation was embarking on an even more audacious quest to not only land on an asteroid, but to bring a piece of it back to Earth. This was the mission of the Japanese Aerospace Exploration Agency's Hayabusa spacecraft, which launched in 2003, bound for the small, stony asteroid 25143 Itokawa. The mission was plagued by technical difficulties that tested the ingenuity of its controllers to the absolute limit. Thrusters failed, orientation wheels malfunctioned, and a small lander designed to hop across the surface was lost. Despite these setbacks, the main spacecraft managed to make 2 brief, harrowing touchdowns on the asteroid's surface in 2005, firing a small projectile intended to kick up dust for collection. It was unclear if the collection mechanism had even worked, and the return journey was an epic saga of survival, with the crippled spacecraft losing communications for months and limping back to Earth on a single, barely functioning ion engine. Against all odds, in June of 2010, the sample return capsule blazed through the atmosphere and landed safely in the Australian outback. When scientists opened it, they found about 1,500 microscopic dust grains. It was a minuscule sample, but it was enough. Analysis confirmed the grains were from Itokawa, providing the first direct sample of an asteroid returned to Earth, and confirming that ordinary chondrite meteorites, the most common type found on our planet, do indeed originate from these S-type bodies. The heroic success of Hayabusa was followed by its successor, Hayabusa 2, and NASA's own OSIRIS-REx mission, which successfully retrieved much larger samples from the carbonaceous asteroids Ryugu and Bennu, respectively. These missions specifically targeted these dark, primitive asteroids because they are rich in the very organic compounds and water-altered minerals that may hold the key to understanding the origins of life. The culmination of this golden age of asteroid exploration was arguably the Dawn mission, a truly remarkable journey that targeted not one, but two of the belt's largest residents. Launched in 2007, Dawn was propelled by revolutionary ion thrusters, which provided a gentle but relentless acceleration that allowed it to perform maneuvers impossible with conventional rockets. Its first destination was Vesta, the second most massive object in the belt, which it reached in 2011. Dawn spent over a year orbiting the protoplanet, confirming its dry, rocky nature and mapping the colossal Rhea Silvia impact basin in stunning detail, providing definitive proof that a specific class of meteorites found on Earth, the head meteorites, were indeed fragments blasted from Vesta's surface. Then, in 2012, Dawn did something no spacecraft had ever done before. It broke orbit with one extraterrestrial body and journeyed onward to enter orbit around another. Its destination was Ceres, the queen of the asteroid belt, the very first object discovered, and the largest by a significant margin. A behemoth so large that its own gravity has pulled it into a nearly perfect spherical shape, earning it the modern classification of a dwarf planet. When Dawn arrived in 2015, it revealed a world starkly different from Vesta. Ceres was dark, cold, and icy, a C-type body through and through. The most stunning discovery was a series of intensely bright spots, shining with the reflectivity of ice, located on the floor of the Akator crater. These spots were found to be salt deposits, specifically sodium carbonate, left behind as briny water from a deep subsurface reservoir had sublimated into space. This was evidence of recent and possibly even ongoing geological activity, a form of cryovolcanism that hinted at a vast, hidden ocean of salty water lurking beneath Ceres's frigid crust. In a single mission, Dawn had visited both a dry, rocky protoplanet and a wet, icy one, the two great archetypes of the asteroid belt, transforming Piazzi's faint star-like points into complex and dynamic worlds. And so, these worlds, once dismissed as mere star-like points of light, have revealed themselves to be archives of cosmic history, each with a unique story to tell. A journey of understanding that has taken us from a simple geometrical puzzle to a complex and vibrant frontier. Our story began with a question, an absence in the heavens, a gap between Mars and Jupiter that, according to the elegant mathematical progression of the Titius-Bode law, ought to have been filled by a planet. This conviction launched a grand celestial hunt in the final years of the 18th century. As a determined band of astronomers the self-styled Celestial Police organized the first truly international scientific collaboration to scan the skies. Yet, before their systematic search could bear fruit, fate intervened on the very first night of the 19th century, when the Sicilian astronomer Giuseppe Piazzi, working alone, stumbled upon a faint, moving light. He named it Ceres, and for a short time, the mystery was solved. The missing planet was found, and the solar system's clockwork was complete. But this neat solution quickly unraveled. The discovery of Pallas just a year later by Heinrich Olbers, followed by Juno and then Vesta, shattered the idea of a single planet. It created a new riddle, not one world, but a multitude of small ones, all occupying the same orbital space. It was Olbers who first proposed a dramatic and, for a time, widely accepted explanation. These were the shattered remains of a single great planet, a hypothetical world named Phaeton that had met a cataclysmic end. For decades, these bodies were considered planets, but their star-like appearance in even the most powerful telescopes led William Herschel to coin a new name for them, a name that would define them for the next 2 centuries: asteroids. This narrative of a destroyed world, while compelling, slowly crumbled under the weight of accumulating evidence. As our understanding of the cosmos deepened throughout the 20th century, we came to realize that the combined mass of every object in the belt would amount to a body far smaller than our own moon, an insufficient mass to ever have been a major planet. Furthermore, the striking chemical diversity among the asteroids, from the dark, carbon-rich bodies of the outer belt to the stony and metallic ones of the inner belt, spoke not of a single shattered parent, but of a diverse population of objects formed in different conditions. The culprit behind the belt's formation, or rather its failed formation, was not an internal explosion or a cosmic collision, but the silent, unyielding influence of its colossal neighbor, Jupiter. This gas giant, the first and largest of the Sun's children, stirred the region with its immense gravity, its powerful resonances sweeping through the protoplanetary disk like a great gravitational broom. It injected chaos into the orbits of the nascent planetesimals, accelerating them to destructive speeds. Instead of gently accreting into a single, larger world, they began to smash into each other with ferocious energy, grinding themselves down in a perpetual cycle of collisional demolition. The asteroid belt, therefore, is not the tombstone of a lost planet, but the preserved cradle of a planet that never was, a collection of primordial building blocks frozen in time, forever denied the chance to complete their planetary destiny. This vast realm, so often depicted as a dense cosmic traffic jam, is in truth a domain of profound emptiness. Its millions of objects separated by millions of kilometers of cold, silent vacuum, a place so sparse that our spacecraft can traverse it with almost no fear of impact. This understanding of a dynamic, evolving region has been sharpened by the discovery of distinct asteroid families, great clans of rock and metal first identified by the Japanese astronomer Kiyotsugu Hirayama, each tracing its lineage to a single ancient collision that shattered a larger parent body. These families, like the scars on the protoplanet Vesta left by the impact that created the Rhea Silvia Basin, serve as a constant reminder that the belt is not a static museum, but an active, grinding mill, a process that continues to this day. And within this landscape of rock and metal, we have found the unexpected glimmer of ice. The discovery of main belt comets, active asteroids that sprout faint tails of dust and gas, has fundamentally altered our view of the solar system's chemistry. These objects have shown that water ice, the most critical ingredient for life as we know it, was not confined to the distant outer reaches of the solar system, but was also present in abundance right here in our own cosmic neighborhood. The chemical signature of this water provides a compelling link to our own world, suggesting that it was asteroids, flung from the belt during the solar system's turbulent youth, that delivered the water to a young, arid Earth, filling our oceans and making our planet habitable. This intimate connection has fueled our desire to know these worlds up close, to move from observation to direct exploration. The pioneering flybys of Galileo, which revealed Ida's tiny moon Dactyl, and the orbital mastery of Aenir Shoemaker at Eros, which culminated in the first landing on an asteroid, opened our eyes to the complexity of these small worlds. The heroic sample return of Japan's Hayabusa from Itokawa, followed by its successor Hayabusa 2 and NASA's OSIRIS-REx, brought pieces of these ancient bodies back to our laboratories, allowing us to touch and analyze the very stuff from which the planets were made. And finally, the grand journey of the Dawn spacecraft, which orbited first the dry, rocky protoplanet Vesta, and then the wet, icy dwarf planet Ceres, has brought the story full circle, transforming Piazzi's faint discovery into a rich and fascinating world. A world with bright salt deposits hinting at a deep, briny subsurface ocean and a geologically active past. The gap in the heavens is no longer a void, but a destination, a region brimming with clues to our past and perhaps resources for our future. The asteroid belt is now seen as a vast, untapped repository of materials that could one day fuel human expansion into the solar system. The same water ice that may have seeded life on Earth could be harvested to provide drinking water, breathable air, and, when split into hydrogen and oxygen, powerful rocket fuel for missions to the outer planets. The M-type asteroids, the exposed metallic cores of shattered protoplanets, are rich in iron, nickel, cobalt, and precious metals like platinum, resources that could be used for in-space construction, manufacturing habitats, spacecraft, and instruments without the immense cost of lifting those materials from Earth's deep gravity well. The belt is no longer a barrier to be crossed, but a potential way station, a logistical hub for a future spacefaring civilization. It remains our most accessible and perfectly preserved archive of the solar system's birth, a chaotic yet beautiful testament to the forces that shaped our planetary home. It is a belt of rubble, yes, but it is also a belt of beginnings, containing the building blocks of planets, the water of our oceans, and the promise of a boundless future among the very stars that first guided us to its discovery. This promise of a boundless future, etched into the very composition of these ancient rocks, is actively shaping the ambitions of the 21st century, shifting the asteroid belt from a subject of purely scientific curiosity into a target of immense strategic and economic importance. The concept of asteroid mining, once the exclusive domain of science fiction, is now being pursued with serious intent by national space agencies and a growing cohort of private companies. The potential prize is staggering, almost beyond comprehension. A single, kilometer-wide M-type metallic asteroid could contain more iron, nickel, and cobalt than has been mined in the entire history of human civilization. Contained within these same bodies are vast quantities of platinum group metals, elements that are exceedingly rare in Earth's crust, but are fundamental to modern electronics, green energy technologies, and catalytic converters. The financial value of a single, well-chosen asteroid is often measured not in billions, but in quintillions of dollars. At the forefront of this new gold rush is the tantalizing prospect of visiting 16 Psyche, a colossal metallic world over 200 kilometers, or 125 miles, in diameter, believed to be the exposed core of a shattered protoplanet. A NASA mission of the same name is currently en route to this metallic giant, not to mine it, but to study it. Yet its findings will undoubtedly fuel the economic case for future resource extraction. The business model for this future industry extends beyond simply bringing precious metals back to Earth. The true value may lie in using these resources in space itself, a concept known as in situ resource utilization. The water ice locked within C-type asteroids could become the fuel and lifeblood of the solar system, establishing refueling depots for missions to Mars and beyond, while the raw metals could be processed by robotic smelters and 3D printers into the habitats, tools, and infrastructure needed for a permanent human presence off-world. Yet for all this incredible promise, the practical challenges of transforming this vision into a reality are monumental, dwarfing even the most ambitious engineering projects ever attempted on Earth. The sheer distances involved are the first and most obvious hurdle. A journey to the main belt is not a short hop. It is a multi-year commitment, demanding spacecraft of exceptional reliability and autonomy. Upon arrival, The environment is unthinkably hostile. There is no atmosphere to shield against the constant flux of solar radiation, and surface temperatures can swing by hundreds of degrees, from over 100 degrees Celsius or 212 degrees Fahrenheit in direct sunlight to less than minus 173 degrees Celsius or minus 280 degrees Fahrenheit in shadow. The primary challenge, however, is a matter of fundamental physics. Operating in a microgravity environment is counterintuitive and perilous. An asteroid's gravitational pull is so feeble that a simple act like pushing a drill against its surface would send the mining vehicle spinning off into space. Any would-be mining operation would first need to securely anchor itself to a spinning, irregularly shaped, and potentially unstable body, a task akin to performing surgery on the tip of a spinning bullet. The most promising theories suggest that many asteroids are not solid, monolithic rocks, but are instead rubble piles, loose agglomerations of gravel and boulders held together by their own weak gravity. Attempting to drill into such a body could cause it to behave like a celestial sandcastle, its structure shifting unpredictably or even breaking apart entirely. Overcoming these obstacles will require radical new technologies in robotics, artificial intelligence, and remote operation, creating fleets of autonomous machines that can navigate the belt, identify promising targets, anchor themselves, and extract and process resources with minimal human intervention. This drive to develop the technologies capable of operating in and around asteroids is motivated by more than just economic opportunity. It is also fueled by a profound and primal instinct for self-preservation. The same gravitational nudges from Jupiter that prevented a planet from forming in the first place are still at work today, constantly flinging asteroids out of the main belt and onto new trajectories. Some of these are cast into the outer solar system, but others are sent careening into the inner solar system, their orbits crossing that of Earth. These objects, known as near-Earth objects, or NEOs, represent the most significant, predictable, natural existential threat to life on our planet. The geological record is a stark testament to this danger. 66 million years ago, an asteroid estimated to be 10 kilometers, or 6 miles, wide, slammed into the Yucatan Peninsula, triggering the mass extinction event that ended the reign of the dinosaurs. More recently, in 1908, a smaller body, perhaps only 60 meters or 200 feet across, exploded in the atmosphere above the Tunguska region of Siberia with the force of 1,000 Hiroshima bombs, flattening over 2,000 square kilometers, or nearly 800 square miles, of remote forest. Had that object arrived just a few hours later, it could have detonated over a major European capital. In response to this clear and present danger, astronomers around the world have established a sophisticated network of survey telescopes, a modern-day celestial police who tirelessly scan the skies every night, cataloging these near-Earth objects calculating their orbits and assessing any potential impact risk. This global effort has already identified over 90% of the largest dinosaur-killing class of asteroids, and thankfully, none of them pose a threat for the foreseeable future. The greater and more statistically likely danger comes from the much more numerous smaller objects, those in the range of 140 meters, or about 460 feet, and larger, which are still big enough to obliterate a city or trigger a devastating tsunami. For the first time in the 4.5 billion year history of our planet, a species has developed the intelligence to recognize this cosmic threat and the technology to do something about it. Having graduated from simply finding these objects, we have now entered the age of active planetary defense. The science fiction dream of deflecting an incoming asteroid has become a scientific fact. In September of 2022, this capability was demonstrated with spectacular success by NASA's Double Asteroid Redirection Test, or DART, mission. The target was a binary asteroid system, a large asteroid named Didymos and its tiny moonlet, Dimorphos, about 160 meters or 525 feet in diameter. Traveling at a blistering speed of over 6 kilometers or nearly 4 miles per second, the vending machine-sized DART spacecraft slammed directly into Dimorphos. The goal was not to destroy the asteroid, but to give it a tiny nudge, altering its orbital period around Didymos by a measurable amount. This technique, known as a kinetic impactor, is conceptually simple. You hit the threatening object with a projectile to change its velocity, and therefore its path. The DART impact was a resounding triumph, altering Dimorphos's orbit by a full 32 minutes, a change nearly 25 times greater than the mission's minimum success criteria. This overperformance was due to the unexpectedly large amount of rock and dust, or ejecta, that was blasted from the impact site, which produced a recoil effect, acting like a natural rocket engine that gave the asteroid an extra push. This real-world experiment provided the crucial data needed to validate our computer models and prove that, given enough warning time, years, or ideally decades, we possess the fundamental technology required to deflect a hazardous asteroid and protect our world from a catastrophic impact. Our relationship with the asteroid belt is thus a profound duality. It is simultaneously a source of immense promise, offering the resources for our future expansion into the cosmos, and a source of profound peril. A celestial shooting gallery that reminds us of our own vulnerability. Mastering the art of navigating and manipulating these small worlds is therefore not just a matter of ambition, but a matter of survival. This dual purpose, the entwined quest for knowledge and for self-preservation, has been the engine of our entire relationship with this celestial realm, transforming it from a mere astronomical curiosity into a place of profound relevance to the human story. The journey to understand the asteroid belt has, in many ways, been a journey to understand ourselves, a cosmic reflection of our own technological and intellectual evolution. We began as distant observers, armed only with our eyes and our theories, trying to impose a sense of mathematical order on the heavens. The Titius-Bode law was a product of its time, a beautiful and compelling idea born from an age that sought clockwork perfection in the universe. When the sky did not conform to this neat pattern, offering a swarm of small worlds instead of a single grand one, we adapted our story, inventing a dramatic tale of a shattered planet. And when that story, too, was found wanting, we looked deeper still, using the laws of physics and the power of computational modeling to uncover a far more subtle and fascinating truth: the story of a world that could never be. A planetary embryo forever held in stasis by the immense and silent influence of its neighboring king. Each step in this journey has demanded more of us, pushing us from the quiet observatory to the bustling clean rooms of spacecraft assembly, and from the chalkboard of orbital mechanics to the high-stakes, real-time control of robotic explorers millions of kilometers from home. Our story, then, has taken us across the immense and silent gulf between Mars and Jupiter, a space that is no longer a void in our minds, but a richly populated and dynamic frontier. We began with the mystery of a missing planet, a puzzle that captivated the astronomers of the 18th and 19th centuries and led to the organized hunt by the celestial police. We witnessed the serendipitous discovery of Ceres by Giuseppe Piazzi, a moment that seemed to bring perfect resolution, only to have that simplicity shattered by the subsequent discoveries of Pallas, Juno, and Vesta. This multiplication of worlds gave birth to the dramatic and long-lived theory of a destroyed planet, a cosmic tragedy that explained the belt as a field of celestial shrapnel. But as our gaze sharpened and our understanding of planetary science matured, a new and more accurate story emerged. We now see the belt not as a graveyard, but as a nursery, a place where the fundamental building blocks of planets were prevented from ever completing their grand assembly. We have identified the great sculptor of this realm, the gas giant Jupiter, whose relentless gravitational stirring and powerful resonances transformed a zone of planetary creation into a zone of perpetual fragmentation, a process that continues to grind and reshape the belt to this very day. Within this grand, chaotic system, we have learned to read the history of our solar system, a history written in the language of chemistry and light. We have categorized its inhabitants, distinguishing the dark, carbonaceous sea types that dominate the outer belt, primitive bodies rich in the organic compounds that form the basis of life, from the stony S-types of the inner belt and the rare metallic M-types, which offer us a tantalizing glimpse into the fiery cores of differentiated worlds that might have been. Through the brilliant insight of Kiyotsugu Hirayama, we have learned to see families among the chaos, great clans of asteroids bound by a shared, violent history, allowing us to trace the echoes of ancient collisions that occurred billions of years ago. And perhaps most profoundly, we found the unexpected presence of water, locked away as ice within the main belt comets. This discovery dissolved the old, rigid boundaries between the dry inner solar system and the icy outer realms, providing a powerful and local source for Earth's oceans, and forging a direct, tangible link between the rocks of the asteroid belt and the emergence of life on our own world. From Piazzi's faint, unsteady light, a single point moving against the static backdrop of the stars, we have journeyed to complex and vibrant worlds, brought into sharp focus by the robotic eyes of our emissaries. We have orbited the battered ancient surface of Vesta, a surviving protoplanet, and walked through our robotic proxies on the dusty, cratered plains of Eros. We have held in our own hands the microscopic grains returned from Itokawa and Ryugu, pieces of another world that have completed an incredible journey to our laboratories. And we have marveled at the mysterious, bright spots of Ceres, the shining salt deposits of a hidden subsurface ocean on a dwarf planet, the undisputed queen of the belt. The gap in the heavens has been filled not by a single planet, but by 1,000,000 stories, 1,000,000 clues to our own origin. It remains a place of duality, a source of potential danger that we are finally learning to defend against, and a source of boundless resources that may one day fuel our journey to the stars. The asteroid belt is the great, unfinished chapter in the story of our solar system's creation, a frozen, silent, and beautiful testament to the delicate balance of forces that allowed our own world to form and flourish, and it will continue to call to us, a belt of beginnings that invites us ever outward into the cosmos. That final invitation to journey ever outward into the cosmos is not an invitation to a solved puzzle, but to a frontier that grows more mysterious and more compelling with every new discovery. For all that our robotic explorers and powerful telescopes have revealed about the asteroid belt, they have also sketched the outlines of even deeper enigmas, questions that challenge the very foundations of our models of planetary science. We have come to know the belt as a place of immense history and potential, but it remains, in many respects, a realm of shadows, its greatest secrets still locked away in the cold silence of interplanetary space. The story of the asteroid belt is far from over. In truth, we may have only just learned how to read the first few words of its epic introduction. The next chapters of this story will be defined not by the knowledge we have already gathered, but by our dedicated pursuit of that which we still do not understand, a quest that begins with the belt's most enigmatic and alluring resident, the dwarf planet Ceres. The Dawn mission gave us a breathtaking first portrait of this world, revealing it to be not just a large rock, but a complex and potentially active water world, a body so rich in ice that it may contain more fresh water than all of the continents of Earth combined. The bright, salty deposits of the Occator crater are the smoking gun of a vast subsurface ocean of briny water, an environment that is dark, cold, and completely alien, but one that may possess all the necessary ingredients for life. Liquid water, a source of energy from chemical reactions in its rocky mantle, and a rich supply of organic molecules, the very same carbon compounds delivered by asteroids like Ceres throughout the solar system. This raises one of the most profound and tantalizing questions in all of science. Could life, in some microbial form, exist today in the hidden ocean of Ceres? It is a possibility that has transformed the dwarf planet from a historical curiosity into a prime target in the search for extraterrestrial life, placing it alongside the icy moons of Jupiter and Saturn as a place where biology might have taken hold. The next generation of space missions now being designed will aim to answer this question, perhaps by sending a lander to the surface to directly sample the bright material venting from below, or by using advanced radar to map the true extent and depth of this hidden global ocean. This great mystery is compounded by Ceres's immediate neighbor and cosmic opposite, Vesta. Why did these two giants of the belt, formed in the same general region of the solar system, evolve along such radically different paths? One became a dry, rocky, volcanic protoplanet, while the other became a wet, icy, and possibly oceanic world. The answer likely lies in the precise location where each body first began to form within the protoplanetary disk, perhaps on opposite sides of the primordial frost line, but the details remain elusive. Unraveling the divergent histories of Vesta and Ceres is more than just a local puzzle. It is fundamental to understanding the chaotic processes of planetary migration in the early solar system and the precise distribution of water and rock that ultimately allowed a world like Earth to become a vibrant, living biosphere. Beyond these two giants, the belt is filled with countless other mysteries. Our classification of asteroids into broad categories like C-type, S-type, and M-type is a useful but ultimately crude simplification. The true diversity of the belt is far greater, a spectrum of compositions that we have only just begun to appreciate. The active asteroids, or main belt comets, are a perfect example. We understand the basic mechanism that drives their activity, the sublimation of exposed ice. But we do not know why only a handful of the thousands of known water-rich asteroids exhibit this behavior. Is it simply that they have been struck by smaller objects more recently? Or is there a more fundamental difference in their internal structure and ice content? And how many more of these dormant, icy bodies are there, waiting for a chance impact to awaken them. The answers have profound implications for our models of how water was distributed throughout the solar system, and how much of it remains locked away in this vast celestial reservoir. There is also the enduring puzzle of the asteroid families themselves. While we can trace their origins to ancient collisions, the exact nature of their parent bodies often remains obscure. By studying the scattered fragments, we are attempting to reconstruct the geology of worlds that no longer exist, piecing together the internal structure of protoplanets that were destroyed billions of years ago. Perhaps the grandest of all the remaining mysteries, however, is the question of the belt's own origin story. The consensus that Jupiter's influence prevented a planet from forming is a powerful and well-supported theory, but it leaves open the question of what was there before the gas giant's intervention. Sophisticated computer simulations, such as the Grand TAC model, suggest that the primordial asteroid belt was once far more massive, perhaps containing as much material as the Earth itself. These models also propose that Jupiter did not form in its current orbit, but migrated significantly, sweeping inward toward the Sun before tacking back outward to its present location. During this epic journey, its immense gravity would have acted like a cosmic snowplow, scattering the vast majority, perhaps more than 99.9% of the original material out of the belt. Some of this material was thrown into the Sun. Some was ejected from the solar system entirely, and a significant portion was flung inward, contributing to the late heavy bombardment that pelted the young Earth and the other terrestrial planets. The asteroid belt we see today in this view is not a pristine sample of the original building blocks of the planets, but is instead the last, tiny, surviving remnant of a once mighty population, a ghost of a planetary mass that was almost entirely scoured from the system. Verifying these models and understanding the full scale of this lost mass is one of the highest priorities for planetary scientists, as it is the key to understanding the violent and chaotic environment in which our own world was born. The quest to solve these riddles is the next great phase of our journey into the belt, a journey that will require even more ambitious missions and more innovative technologies. It is a quest that is inextricably linked to our own survival and our future in space. To defend our planet from a hazardous NEO, we must understand its composition. Is it a solid block of iron we need to push, or a loose rubble pile that might fragment if we hit it too hard? To build a thriving economy in space, we must know where to find the most accessible deposits of water and the richest concentrations of precious metals. The scientific and the practical are, and have always been, two sides of the same coin of exploration. The asteroid belt has been our constant companion on our journey to understand the solar system, and it will continue to guide us as we venture further out into the great star-filled ocean of the cosmos. Our journey through this celestial realm has thus brought us full circle. From a simple question of cosmic geometry to a deep and intricate understanding of our own planetary origins. The call to venture ever outward is a call to read a story that is 4.6 billion years in the making. A story written in the silent language of stone, metal, and ice. We began with a perceived emptiness, a gap in the heavens that demanded a solution, a missing piece in the elegant clockwork of the solar system envisioned by the astronomers of the Enlightenment. This quest led us to a single point of light, Ceres, which for a fleeting moment seemed to bring order to the cosmos. But the universe is rarely so simple. The discovery of its brethren shattered this tidy picture, replacing the ghost of one missing planet with the dramatic specter of a shattered one. For over a century, this idea of a lost world held sway, a compelling narrative of cosmic catastrophe. Yet, as our tools and our theories grew more sophisticated, we uncovered a more profound and fundamental truth. The asteroid belt is not the remnant of a world that was, but the fossil of a world that could never be. We have come to know its true architect, the silent gravitational hand of Jupiter, which stirred this region into a state of perpetual chaos, ensuring that the planetary building blocks would forever remain just that, the raw, unassembled material of creation. From this grand, overarching narrative, we have zoomed in to see the intricate details of this diverse and ancient population. We have journeyed with robotic emissaries that transformed these faint, star-like points into tangible, complex worlds. We have witnessed the stark contrast between the dry, battered, and rocky protoplanet Vesta, a survivor of the solar system's violent youth, and the dark, icy, and mysterious dwarf planet, Ceres, a world so rich in water that it may harbor a hidden global ocean beneath its frigid crust. We have learned to see the echoes of ancient collisions in the great families of asteroids, tracing the scattered debris back to ancestral parent bodies that were destroyed in catastrophic impacts eons ago. And in the most surprising discovery of all, we have found water where none was thought to exist, in the faint, ghostly tails of the main belt comets. This has forged an undeniable link between this seemingly desolate region and our own vibrant blue world, suggesting that the very water that fills our oceans and courses through our veins was delivered to a young Earth by bodies born in this celestial rubble field. We have even reached out and touched these worlds, bringing back precious grains of dust from their surfaces, samples that have confirmed our theories and allowed us to hold a piece of the solar system's primordial past in our own hands. In coming to know the asteroid belt, we have also been forced to confront our own place within this dynamic cosmic system. We now understand that the same gravitational forces that shape the belt are capable of sending its inhabitants on trajectories that cross our own, posing the only predictable, large-scale natural threat to our long-term survival. This recognition has spurred us to become guardians of our own planet, developing a planetary defense network that scans the skies, and a technology proven by the success of the DART mission that gives us the power to deflect a potential impactor. We are the first species in Earth's long history capable of preventing its own extinction-level event. At the same time, we look to the belt with a sense of immense opportunity. The same bodies that pose a threat are also a vast and untapped repository of the resources we will need to build a future for humanity beyond our home world. The water ice needed for life support and rocket fuel, and the countless tons of precious and industrial metals locked within these cosmic stones could form the very foundation of a sustainable spacefaring civilization. The asteroid belt is thus a place of profound duality, a source of both peril and promise, a constant reminder of our cosmic vulnerability and a beacon of our boundless potential. Our exploration of this region, therefore, is more than just a scientific endeavor. It is a fundamental part of the human journey. The gap in the heavens is no longer a void, but a mirror reflecting our own past and a window into our future. It is the great, unfinished story of planetary formation, a perfectly preserved archive of the conditions that gave rise to our home, and a crucial signpost that will guide our next steps into the solar system. The questions that remain, the true nature of Ceres's hidden ocean, the full story of the belt's lost mass, the sheer diversity of its millions of undiscovered inhabitants, are the questions that will drive the next generation of explorers, engineers, and scientists. From a simple mathematical curiosity, the asteroid belt has revealed itself to be a place of immense complexity, beauty, and importance, a bridge connecting the fiery birth of the sun to the dawn of life on Earth. And now, to our own first tentative steps into a wider cosmos. It is, and has always been, a belt of beginnings.